When a massive star runs out of nuclear fuel, it can no longer support its own weight. The core collapses inward, triggering a massive shockwave that violently ejects the outer layers of the star. Left behind in the void is a rapidly spinning remnant. This remnant is compressed to an extreme degree. The matter density inside this core exceeds 2.7 times 10 to the 14th grams per cubic centimeter. That is significantly denser than normal nuclear matter. Mapping its outer layers, beneath a thin atmosphere lies the outer crust, transitioning through an inner crust into the outer core. But pushing deeper past established nuclear theory, the inner core's precise subatomic composition remains completely unresolved. Because these supernuclear densities require gravitational forces that cannot be replicated in any laboratory on Earth, the exact internal architecture of the densest objects in the universe remains completely unknown. To solve this, astrophysicists rely on the equation of state. This is the mathematical rulebook that dictates exactly how matter behaves, compresses, and holds its structure under extreme pressure and density. There are several competing models for the core's equation of state. Some propose it is made entirely of standard homogeneous nucleonic matter. Others suggest the immense pressure forces particles into exotic phases, like exotic hyperons, strange quark-matter, or Bose-Einstein condensates. Introducing these exotic particles changes the macroscopic properties of the star. Specifically, exotic matter typically makes the equation of state softer, meaning the core compresses much more easily under the crush of gravity. Since we cannot extract a sample of the core to test these theories, we have to look outward. We must observe massive, macroscopic astrophysical events and use that data to reverse engineer which microscopic equation of state accurately describes reality. The first step is translating the microscopic math into observable properties. Physicists use the Tolman-Oppenheimer-Volkoff equations to calculate exactly what mass and radius a theoretical equation of state will produce. This chart plots predicted neutron star masses relative to their radii. When theorists model equations of state containing exotic matter, the results create a contradiction. The exotic matter softens the core so severely that gravity should overcome it, collapsing the star into a black hole before it can reach even 1.5 solar masses. But observational astronomy provides a strict boundary. Astronomers have accurately measured the mass of highly stable pulsars at 2.01 solar masses, with a margin of error of just 0.04. To keep exotic matter models viable under this constraint, physicists have to introduce strong repulsive forces into the math, such as phi-meson exchange. This theoretical adjustment stiffens the equation of state, pushing back against the inward pull of gravity. This 2 solar mass limit filters the theoretical models. It proves that if exotic particles like hyperons do exist inside the core, their governing equation of state must be highly stiff to prevent a total gravitational collapse. While maximum mass gives us a ceiling, it still leaves multiple equations of state on the table. To narrow the field further, we have to observe what happens when 2 neutron stars orbit each other and eventually merge.
The equation of state directly dictates the physical volume of these stars. A stiff equation produces a larger characteristic radius, while a soft equation results in a smaller, highly compact sphere. This difference in volume dictates their orbital mechanics. Larger, stiffer stars will begin to interact at a distance, but smaller, softer stars can achieve a much tighter orbital separation, accelerating to higher velocities before they finally touch. Because the softer stars get closer and move faster before their gravitational fields tear them apart, they violently disrupt each other upon impact. This orbital geometry means a softer equation of state guarantees a far more destructive collision. The increased velocity amplifies the shock heating and drives intense kinetic oscillations through the merged remnant. That amplifies shock heating has a direct physical consequence. It forcibly ejects a significantly larger mass of neutron-rich material out of the gravity well and into deep space. Once free from the core, this material undergoes the rapid neutron capture process, or R process. In a fraction of a second, atomic nuclei absorb free neutrons to forge highly unstable heavy elements beyond iron. As these newly synthesized heavy isotopes undergo radioactive decay, they release an immense amount of thermal energy. This powers a brilliant, short-lived optical and infrared flash known as a kilonova. This scatterplot displays the relationship between a neutron star's characteristic radius and the peak luminosity of its kilonova. There is a clear inverse relationship.
Smaller radii, derived from softer equations of state, yield massively higher peak luminosities. The scale of this effect is highly distinct. Models using a soft equation of state, like SFHO, predict a kilonova that is nearly 3.7 times brighter in the infrared band than one produced by a stiff equation, like DD2. Therefore, the peak brightness of a fading kilonova acts as a direct, observable proxy for measuring the subatomic stiffness of the neutron stars that were destroyed to create it. In 2017, astronomers recorded a historic multi-messenger event. The gravitational wave signal GW170817 followed immediately by its accompanying kilonova, designated AT2017-GFO. Observations of this kilonova revealed an exceptionally high peak luminosity. The light curve data indicates the collision-synthesized 0.05 solar masses of heavy R-process nuclei. This massive volume of ejected material and the resulting brilliant emission profile strictly support a softer equation of state. The gravitational wave data corroborates this. By measuring the tidal deformability of the two stars during their in-spiral, physicists independently constrain their radii to under 13 kilometers. By combining the kilonova light curves with gravitational wave telemetry, astrophysicists can definitively rule out the stiffest theoretical models, narrowing the search for the true nature of the inner core. We are tracking the radioactive decay of heavy elements, forged in collisions millions of light-years away, to map the subatomic dynamic landscape of dense nuclear matter. This multi-messenger approach, layering light, gravity, and nuclear physics, is the only physical method we have to solve the equation of state. Multi-messenger astrophysics has turned the neutron star into a high-energy particle physics laboratory at a cosmic scale.